So in this particular video, I'm going to discuss about the heat of combustion values based on which we can explain the stability of cycloalkanes. This particular topic has been pulled out from the degree first semester syllabus, that is Alicyclic hydrocarbons chapter 6. The whole chapter has been discussed on my YouTube channel, and the details of this playlist has been given in the description box below. If you like this, please do like, share, and subscribe my channel. Yes, it before understanding stabilities of cycloalkanes based on these heats of combustion values, let's understand what is this heat of combustion. This heat of combustion is nothing but the amount of heat released when 1 mole of a substance is burnt in the excess of oxygen to carbon dioxide and water. So, for suppose if CnH2n, this is cycloalkane, is burnt, then 3 by 2 N of oxygen molecule is required, resulting in the formation of NCO2 and N water molecules, and certain amount of heat is released, which is nothing but because of this is a negative sign because heat is released. Uh, and there is a certain amount of heat is released, that is n times the energy per CH2. So this is what is heat of combustion. Now let's do this in detail further in my further slides. Yes. Now the amount of heat released, for example, for cycloalkanes, per CH2, it is 658.6 kilojoules per CH2, and this is obtained from an unstrained long chain molecule. So if you take this unstrained long chain molecule, the amount of heat released per CH2 here is 658.6 kilojoules. And based on these heats of combustion values, now we can explain the stability of cyclohexanes, or for that matter, any other higher members in the series. So this is nothing but we can explain the thermochemical stability and the total strain which is associated with the molecule with the heats of combustion values. So now, based on these heats of combustion values, now we can say that if the size of the ring is changed from, the cyclopropane or cyclobutane, and as the size is increasing, then the heats of combustion values will also change. And in other words, the strain which is associated with that particular molecule will be reflected in the heats of combustion values. So, based on the states of combustion values, we can explain the suitability of Bayes strain theory, and we can verify this based on, Bayes strain theory based on this heats of combustion values of different cycloalkanes. So when we look at this chart now, so we can understand this heat of combustion values in detail, and we know that for an ideal molecule from an unstrained long chain molecule or long chain alkane, the amount of heat released, or the heat of combustion value, is 658.6 kilojoules per mole, and I've already said that in my previous slide. So and if you take cyclopropane, that means the ring size is 3 here, that means 3 carbons arranged in a cyclic manner. Then the heat of combustion which is released, all these are in negative values here. Per CH2, it is 697.1 kilojoules per mole. That is per CH2, and for total molecule, that means it is 2091 kilojoules. That means multiply with 3 because the ring size is 3 here. And for cyclobutane, it is 686.1, and total is 2744 kilojoules. That means into 4 here, because the ring size is 4. In the same way, for cyclopentane is 664.0 kilojoules, and heat of combustion, the total heat of combustion for the molecule is into 5, that is 3 into 5 here. So it is 3320 kilojoules. In the same way, for cyclohexane is 658.6, and when we observe this, this is nothing but the value which have changed from an unstrained long chain molecule. This 658.6, that means it is totally relieved from strain here. See, I've circled this. Uh, this one, it is totally relieved from strain, which means that there is no strain in the molecule, as this is a reference for a long chain, I mean unstrained molecule here. Yes. And for cycloheptane, it is 4637 kilojoules, and for cyclooctane, it is 5309 kilojoules for the total molecule. And when we look at the ring strain per CH2, it is 38.5 kilojoules per mole. How did we arrive at this? Is 658.6, that is for unstrained molecule, minus 697.1, which is nothing but 38.5. This is per CH2, and for the total ring strain is, it is into 3 here. So it is 115. In the same way, for cyclobutane, it is 27.5, and for the total molecule, it is 110. And for cyclopentane, 5.4, and for total molecule, it is 27. And when you look at this, it is zero ring strain. There is no strain in the molecule here for cyclohexane. I'm underlying this. So just remember this in our further discussion. And for cycloheptane, that is 3.8, and so on. Uh, uh, this is increasing now a little. And now how this uh, based on these heats of combustion values, now look at this facts to explain the Bayer strain theory. I mean, how this Bayer strain theory is, how far it is suitable to explain the cycloalkane stability. We can see this. For example, when you take the cyclohexane here, I've already said this, the heat of combustion value here for cyclohexane, it is 658.6 kilojoules per mole. This is for, I said this is for an unstrained long chain molecule. So there is zero strain in this molecule. That means that is free from ring strain, or any other strain, that is for that matter, angle strain or torsional strain or whatever. So cyclohexane is the most stable among all the cycloalkanes according to this heats of combustion values, but this is not in agreement with the Bayer's theory. What Bayer said is, according to Bayer, it was cyclopentane was more stable, but according to the heats of combustion values, the cyclohexane is more stable. So the reason is Bayer assumed that the cyclohexane to be planar, so there's certain amount of ring strain which is associated with it because of this uh, angle which is 120 degrees. So there's a deviation from this bond angle, so that is ideal angle, that is 109 degrees 28 minutes. But according to Bayer, it was planar structure, but but in reality, this is assuming the shape is a pucker shape, which is nothing but it is assuming the uh, chair conformation, where the bond angle is 109.5 degrees. So it is having an ideal bond angle of 109, that's a tetrahedral bond angle of 109. So thus relieving totally from the angular strain. There is no angular strain, and also all the hydrogens and all the carbon atoms are in staggered conformation. Therefore, there is free from angular strain, and uh, free from torsional strain. So it is totally free from all the strains. That is no ring strain which is seen in this molecule here. So this is not in agreement with the Bayer's theory. The Bayer assumed that uh, cyclohexane was flat, so there is certain amount of angular strain, but in reality it is having a puckered shape, where it is attaining the ideal bond angle, so there is no angular strain, or for that matter no torsional strain, because all the hydrogens are in staggered conformation. So now when we look at cyclopropane here, according to the heats of combustion values, let's go back to this once again, to this, yeah, heats of combustion values. When we look at for this cyclopropane, the ring strain we have seen is 38.5 kilojoules per mole, that is per CH2 group, and the total ring strain is 115 kilojoules per mole. So 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 per CH2 group is 38.5 kilojoules per mole. So this ring strain is because of the angle strain and also because of this torsional strain in cyclopropane. And so the bond angle here, that is not ideal bond angle. The bond angle should be 109.5, but here it is only 60 degrees here. So there is certain amount of ring strain, and also the hydrogens on this adjacent carbon atoms are in eclipse conformation and not in staggered conformation. So it is suffering from torsional strain also. So there is two types of strain which is present here, angular strain and torsional strain. The molecule is not stable here. So this is an agreement with the Bayes theory. So Bayes strain theory could explain this totally, the stability of cyclopropane, and this can be explained based on the heats of combustion values also. So out of all the cycloalkanes, cyclopropane is the more reactive one, and in order to relieve from this strain, it undergoes this addition reactions, that is the ring opening reactions, to relieve from this strain. So it react with Br2, HBr and H2 to give the addition products. For example, the cyclopropane reacts with HBr to give the ring opening addition product. Yes. And when we come to the cyclobutane, according to the heat of combustion values, we have already said. So let's go back to the chart once again. Yes, when we look at this cyclobutane here, see, the heat of combustion values is 27.5. So per CH2, that means the ring strain per CH2. So the ring strain is slightly decreased here from here to here. So it is decreased from cyclopropane to cyclobutane. So according to the heat of combustion values, cyclobutane is more stable than cyclopropane. So the cyclobutane is much more stable than cyclopropane, and so it's associated with lesser amount of strain, and this is an agreement with the Bayes strain theory. So Bayes theory could also explain the stability of cyclobutane then compared to that of the cyclopropane, and is much less reactive than cyclopropane. And when we come to the cyclopentane, according to this heats of combustion values, the ring strain is 5.4 kilojoules, and the total ring strain, as it is having the cyclopentane is having 5 carbon atoms, so it is 27 kilojoules for the total molecule. Uh, so it is having the ring strain of 27 kilojoules, and this is not in agreement with the Bayes strain theory again. So Bayes theory said that cyclopentane is the most stable of all the cycloalkanes, but heats of combustion values say that cyclopentane is less stable than cyclohexane. So cyclohexane is more stable than cyclopentane. This is according to the heats of combustion values. But according to the Bayes theory, it's other way around. So it could not explain the stability of the cyclopentane. So, but why this is happening is, in order to, this according to Bayes theory, the cyclopentane should be flat or planar, but this is reality is not flat. because there is lots of torsional strain or eclipse strain in between the hydrogens here. So in order to relieve from this strain, this one is training the puckered shape, that is non-planar, that is an envelope shape where the hydrogens, they are relieving from the torsional strain. That's the relief from this torsional strain in this conformation. So the molecule is not planar in reality, which Bayer said it to be planar. Uh, so it is having no, it is not having angle strain according to the Bayer's theory, but in order to relieve from this torsional strain, it is assuming this uh, non-planar conformation where the fifth carbon atom is above and below the plane. It looks like an envelope here. So it's have no angle strain but very high torsional strain, because of which the cyclopentane is less stable than cyclohexane. This is how we could explain the stability of the different cyclohexanes based on the heats of combustion values. So cycloalkanes with 6 or more carbon atoms are equally stable and are strainless, and this is in contrast to Bayer strain theory. So it is totally contrast to Bayer strain theory, according to which Bayer said that the higher, I mean, the ring systems with 6 or more than 6 carbon atoms are unstable and do not exist, but in reality they are stable and strainless.